Hey everyone, and welcome to The Explainer. Today, we're going to talk about everything that spins, twists, and turns. I mean, think about it. From planets going around the sun to a simple spinning top, there's this one single principle that's running the whole show. So let's figure out what it is.
All right, let's start with something we all get. Pushing things in a straight line. You go to push a shopping cart, it takes some effort. But then you try to push a car, yeah, that's a whole different story. That thing that's resisting you, that property that doesn't want to move, that's its mass, or, inertia. Pretty straightforward, right?
Okay, but what happens when we're not pushing anymore, but we're trying to spin something? I mean, why is it so easy to spin a pencil between your fingers, but try doing that with a heavy barbell? No way, right? Well, it turns out there's a rotational version of mass, a property that fights back when you try to spin it. And figuring that out, that's the key to this whole explainer.
So yeah, that resistance to being spun, it's got a name, the moment of inertia. Just think of it like this. It's the twin brother of mass, but for the world of rotation. You could even call it the rotational laziness of an object. And honestly, it's the star of our show today. And what's so cool here is how neatly physics just mirrors itself. Look, in straight line motion, you have a force that makes something with mass speed up. Okay, in rotational motion, you have a torque, which is really just a fancy word for a twisting force, that makes an object with a moment of inertia spin faster. See the parallel? Mass and moment of inertia are playing the exact same role, just in different kinds of motion. So if we're gonna get formal about it, the moment of inertia is how much an object resists changes in its rotation. The bigger the moment of inertia, the more twisting force, or torque, you're gonna need to get it spinning faster or to slow it down. It is, quite literally, its rotational laziness. Okay, so if it's the rotational version of mass, does that just mean it's all about how heavy something is? Nope. Not even close. And listen up, because this is probably the single most important idea we're going to talk about. It's not just how much mass an object has, it's where that mass is. And you can see why, right in the formula. To figure out the moment of inertia, you basically take every little speck of mass in an object, and you multiply it by its distance from the center of rotation, squared. And that squared part, oh, that's a huge deal. It means that how far away the mass is matters way, way more than the mass itself. If you double the distance, you actually quadruple its effect on the object's resistance to spin. It's a game changer. Let's make this super clear with a simple rod. Imagine spinning it right around its center. Most of the mass is, on average, pretty close to the middle, right? So it has a fairly low moment of inertia. It's not too hard to spin. But now, take that exact same rod, same weight and everything, and try to spin it from one of the ends. All of a sudden, most of its mass is way far away from the point of rotation. The result? A much, much higher moment of inertia. It's way harder to spin. Same object, same mass, but a totally different feel when you try to rotate. All right, now let's see how this plays out in one of the most beautiful and, frankly, famous examples in all of physics. Seriously, if you've ever watched figure skating, you've seen moment of inertia put on a masterclass.
So, you know the move. A figure skater starts a spin, arms stretched way out. And then, bam, they pull their arms in tight to their body, and suddenly they're a blur. They're spinning incredibly fast. Now, that's not some kind of magic trick. It's pure physics.
Think about it. When her arms are out, she's deliberately putting her mass as far away from her center of rotation as she can. That gives her a really high moment of inertia. But the second she pulls her arms in, she's bringing all of that mass close to the center, which causes her moment of inertia to drop dramatically. So why does that make her spin faster? Well, it comes down to a fundamental law of the universe, the conservation of angular momentum. You can think of angular momentum as the total amount of spin energy an object has, and for that skater, that total amount has to stay the same. So if she drastically lowers her moment of inertia by pulling her arms in, her spin speed has to go way up to keep the total spin energy balanced. It's a trade-off. Less resistance to spin means more spinning speed. Simple as that. And this isn't just for putting on a good show at the Olympics. This principle is absolutely critical in engineering and design. I mean, it's everywhere. Engineers are constantly, intentionally playing with an object's moment of inertia to make things work just right. But before we get into those examples, let's just quickly nail down what torque is. If moment of inertia is rotational mass, then torque is rotational force. The best way to think about it is riding a bike. Torque is how hard you have to stomp on the pedals to get them to turn. Power, on the other hand, is how fast you end up going because of it. So high torque is all about raw, brute turning force. So how do engineers put this to work? Well, a flywheel inside an engine is designed to be heavy and wide, with a really high moment of inertia. Why? To resist changes in speed and keep the engine running smoothly.
On the flip side, a combat jet is built with a super low moment of inertia. It's all about making it easy to change direction, to roll and pitch incredibly fast. Think about a tightrope walker. They use that long pole to increase their moment of inertia, making them way more stable and much harder to tip over. And then, you've got a big truck engine. That's designed for one thing: massive torque, that raw rotational force you need to get a super heavy load moving from a dead stop.
So as we start to wrap this up, it's pretty clear this isn't just some formula you memorize for a test, right? This is a fundamental concept that literally shapes how things move on every single scale you can imagine. In the end, moment of inertia is really the architect of spin. It's not just about what an object is made of, it's about how that stuff is arranged. You change the shape, you change the spin. And that simple idea controls the motion of entire galaxies, the performance of an athlete, and how the machines we build every single day actually work. So the next time you see a kid on a merry-go-round scoot to the middle to speed up, or you watch a pizza chef tossing dough in the air, you'll know what's really going on. You'll see the secret. It's all about the moment of inertia. And that just leaves one question. What else are you going to see spinning in a whole new light now? Thanks for joining me.